Okay, so this is going to be short, but this is just something that I thought was interesting. So I we've seen before how you can solve the XOR problem with the TensorFlow-Quantum and quantum variational circuits. And so um, clearly it labels the four, binary inputs correctly, but I was wondering what the decision boundaries actually looked like. Um, really just out of curiosity because I had to do a lot of decision boundaries for class. And so um, before we plot the decision boundary, in some range, we have the 4 points, and then we want to um, see where, on that sort of Cartesian graph, it thinks is 1 and where it thinks is -1 or 0 and 1 in binary. And so that requires a couple of updates to the original code. And so this is quick. Everything is pretty much the same. The convert data, the circuit, the accuracy, all of this stuff is the exact same. There's only really two differences. The first is that we need to make the training data creation more flexible, specifically because last time it was hard coded into just 00100111. You couldn't input other points to get an approximation of the decision boundary, and so and we have to approximate it since um, I don't know, it's probably possible theoretically, but I don't know how to analytically solve for the decision boundary in a quantum circuit, and so um, the idea is pretty simple though, because we have this convert data here. Um, Last time, if you remember, it was just the Pauli X gate applied either not at all or just normally applied for ones. And so this would be just two identity gates, and this was two Pauli X gates. And so we can change that to just be Pauli X gate to the power of the input. So for 0, anything to the 0 power is just 1, which is just the identity gate there. And anything to the first power, anything to the first power is just itself. And so that'll just be the normal X gate. But this allows for intermediate forms. Um, so that it doesn't change anything about these inputs. These actually become reduced to the exact same thing they were last time. It just enables more points to be put in. And so why that matters is if we go down here, after all of that, the way we approximate the decision boundary is we make a mesh grid. So we create a bunch of points in this area. In this case, this takes a while to run because of this function here. But so you can decrease this, but do note it still takes a while. This is the number of points that you're creating. And so what you do is you just make a mesh grid, and then for each point, you have to predict what that point will look like. And then you can plot the color mesh, and you can see the decision boundary. And so this takes a while because it has to guess for every single point. And well, the real hard part is actually just you have to convert the data for every single point. And so that's kind of, even if you did batching and ran this function on every single input point and just created the array from there, it would still be challenging because, or computationally expensive because you have to convert the data for every single one. But other than that, that's pretty much the only differences is just this code here, which I've basically, I just took from some of my homeworks I've done in the past, and to update the inputs so that the power here enables not just 0 or 1 input. So just remember that the x to the I gate equals Rx. That's basically equivalent because you're saying if I is 1, then you're rotating at pi, which is just 180 degrees. And so that's pretty much That's pretty much the only differences. So when we look at this, we see that this is what the resulting decision boundary is. If I can zoom in a little bit. And this is really interesting. So we see here, it's nonlinear. There's a 0, 1, which is XOR, and 1, 0 XOR, and then these two are different. And so this is interesting because if we had something like the canonical 2-layer neural network do this, the decision boundary, I don't have it. That might be a good idea to have. Would be something like a line here and a line here. And this is interesting, especially because, I mean, not that this would be practically relevant, but trying to like even this simple function, there's just 12 parameters in this quantum circuit. Trying to fit a neural network that would recreate this output would probably be pretty challenging, because if you notice, there's lots of little bubbles in here. If you zoom in even further, you can see there's all sorts of little interesting areas. And so I do wonder, maybe if you want to try different things with the code, which I'll make available, if you try expectation value instead of sampling, or so if I go back, here I do 32 samples. You could change this to an expectation layer. You could change it to few more samples. Those are all interesting things that might be worth trying out. I honestly don't know what they will look like, but I did think that this decision boundary was interesting, and so I just wanted to share it.